Welcome to lesson 17 of topology. We're going to talk about bases for topological spaces in this lesson. You may remember in one of the earlier lessons I briefly introduced bases and I said I would get to them in more detail later on. So this is the later on that I talked about. In the first sentence is the definition I gave much earlier in this series of lessons on topological spaces, but let me repeat it here. A base or basis for a topology tau of a topological space x, tau is a collection B taken from tau such that every open set of the topology is equal to the union of some elements of B. So it's basically a way of generating your entire topology from some subset of the open sets. For example, the set of all open intervals in the real number line R is a basis for the Euclidean topology on R, because every open interval is an open set, and every open set of R can be written as a union of open intervals. So we have our first example. That you can also think of the open balls from a metric space. That would give you a base for your metric space. Bases are ubiquitous throughout topology. The sets in a base for a topology, which are called basic open sets, are often easier to describe and use than arbitrary open sets. Yeah, and as I just mentioned here, but I'll read it again. For example, the open balls in a metric space, which do in fact form a base, are easy to describe and use versus the collection of all possible open sets in a metric space. Many important topological definitions, such as continuity and convergence, can be checked using only basic open sets instead of arbitrary open sets. In general, a topological space can have several different bases, so they're not unique. The whole topology tau is always a base for itself, but obviously it's typically the most verbose space. Further, two different bases need not have any basic open sets in common. The following theorem gives us a condition for determining whether or not a collection of subsets of a topological space is a base. Well, let's have a look at the theorem. A collection B of open subsets of a topological space X is a base for a topology of X if and only if for each element X in our topological space and each neighborhood U of X there exists V in our collection of sets B such that X is an element of V and V is a subset of U. So I drew it here just to help visualize. So you have X and then you have a neighborhood U about X, and this condition here is saying there needs to be in order for B to be a base, there needs to be some set from B that's within U and which also contains X. So let's prove that. Let's start with the if B is a base of X. So going in the forward direction here in this if and only if statement. If B is a base of X, then each open neighborhood U of X is a union of sets from B, and so there must be some V and some subset V, which is an element of our base, our set V, such that X is an element of V, is a subset of U. So that proves the theorem going forward direction. Now let's prove this condition holds here. Then take any open set U of X. For each X an element of U, there exists V sub X an element of B, such that X is an element of V sub X is a subset of U. Right? That comes from our condition here. And then clearly U is the union of all these V sub X. So any open set X of X is a union of sets from B, and therefore B is a base for our topology. So we have this proven. As noted, it's sometimes easier to define a topology on a set X by specifying a base for that topology. However, not every collection of subsets of X are a base for a, I should say, is a base for a topology. It is necessary to check that the proposed base satisfies the conditions of the following theorem. So let's talk about that on the next slide. We have another theorem concerning conditions under which a collection of subsets of a set X form a base in a topology on set X. So we have the theorem written out here. Let's read it. A collection of subsets B taken from a set X is a base for a topology on X if and only if it has the following properties. Each X, an element of X, is an element of at least one set in B. If U, V are elements of B, and X is an element of the intersection of U and V, then there exists W in our collection B such that X is an element of W and W is a subset of the intersection of U and V. So we'll prove it in the forward direction first. Assume the subsets B form a base for a topology on X. Since X is a topology, we know it's open, and it must be the union of sets from B in that case. It's just by the definition of a base. Thus, each X, an element of X, is an element of at least one member of B. So that gives us the first property here. Then property 2 holds since U and V is open and is thus the union of members from B, at least one of which contains X. Remember, U and V is open. The intersection of U and V is open because going in the forward direction, X is a topological space, and U and V are members of the base, so they're open sets, and the intersection of open sets in a topological space is open. So that's why this is open. Let's go in the other direction. Assume these properties hold. So assume B is a collection of subsets of X for which properties 1 and 2 hold. Let tau be the collection of all subsets of X that are unions of sets from B, including the empty set. So clearly B is a base. However, we still need to show that this topology that we defined here is a valid topology. So we need to show the definition of a topology fits what we've defined. And I'll do that on the next slide. To complete our proof, we need to show that tau is defined on the previous slide. In other words, all the unions of sets from B is a valid topology. So let's do that. By property 1, and I've copied the 2 properties down here so you don't have to flip back. By property 1, X is the union of all members of B. So X is in our topology. And we were given that the empty set was in our topology, so we have those 2 things checked off from the definition of topology. We need to show all unions of sets in our topology are, again, an open set. All union of open sets is open. And we need to show that finite intersections of open sets are open also. So let's do that. Clearly, the union of sets in tau is also in tau, given how we define tau. So it only remains for us to show that tau is closed under finite intersections. To that end, take 2 elements, 2 sets from tau. So these would be open sets, and take any X, an element of the intersection of U and V. By the definition of tau, U and V are each the union of sets from B, and so there exists U sub X and V sub X, an element of B, such that X is an element of U sub X, which in turn is a subset of U, and X is an element of V sub X, which in turn is a subset of V. Thus, X is an element of the intersection of U sub X and V sub X, and by property 2, there exists some W sub X in our collection B, such that X is an element of W sub X, which is a subset of the intersection of U sub X and V sub X, and which in turn implies that W sub X is a subset of the intersection of U with V. So clearly the intersection of U and V is the union of all W sub X, where we take the each X in the intersection U V. And thus the intersection of U and V is also in our topology. So we've done it for 2, but you can just do it for 3 and 4 and 5. It's basically inductions once you prove it for the intersection of 2 sets being also in our topology. So that's our proof. We have a few more definitions in this lesson, and then we'll move on to some other topics. We briefly mentioned second countable spaces earlier. I want to talk a little bit more about them here. The second countable space, also known as completely countable separable space, is a topological space whose topology has a countable base. So that's pretty straightforward. So it could either be a finite number of elements in the base or a countable number. More precisely, a topological space is second countable if there exists some countable collection U, with these sets U sub I and the index is countable, of open subsets of X, such that any open subset of X can be written as a union of elements from a subfamily of U. A second countable space is said to satisfy the second axiom of countability. And I've given a reference down here if you want a little more information on second countable. There's a Wikipedia article, you can look that up. I put the link down here, but if you just do a search on second countable space, you'll probably see the Wikipedia article come up first. There's also something called first countable. That's a bit more obscure. I haven't seen that used very much, and the definition is a bit complex, so I'm not going to cover that here, but I'll give you the reference down here if you're interested. And what many well-behaved spaces in mathematics are second countable. For example, n-dimensional Euclidean space with its usual topology of open balls is second countable. Although the base of open balls is uncountable, one can restrict the collection of all open balls to those with rational radii and whose centers have rational coordinates. So in that case, you do get a countable base. We have a few more definitions before we finish this lesson. These are similar to what we had for metric spaces, but we're going to restate them here in the context of topological spaces. The first definition is open cover. It's pretty easy. An open cover of a topological space X is a collection of open subsets of X whose union equals X. Then a subcover of an open cover C of X is a subset of C whose union is X, so that's also pretty straightforward. A subset Y of a topological space is dense in X if the closure of Y equals X. So recall we had the classic example of the rational numbers being dense in the reals because the closure of the rationals included all the real numbers. A topological space X is separable if there is a countable subset of X that is dense. Second countability implies other important topological properties. For example, every second countable space is separable, we just said here, and something called Lindoff, which is the condition here. Every open cover has a countable subcover. That's called Lindoff. Okay, so that's it for this lesson. We'll take up some concepts in the next lesson concerning separable topological spaces.